I am Rajesh Tangella, Assistant Professor, Department of EEE, Vigyan Nirla Institute of Technology and Science for Women. In the last lecture, I explained about the expressions of inductance for single phase and for three phase, which are of single circuit and double circuit lines. Now, in this lecture, I am going to explain about expression for capacitance for single phase as well as for three phase line. So, in order to derive the expression for capacitance, first we need to know all about what is electric potential. So, the electric potential at a point due to a charge is generally said to be the work done in bringing a unit positive charge from an infinite plane to that particular point. Now, this is said to be the electrical potential at that point. If you write this electrical potential, then by simply taking C equals to capacitance equals to charge per this potential, you can easily get the expression for capacitance. Now, how to write this electrical potential means, see here. So, let us take a conductor of charge QA. Now, let us take a point P, which is at a distance of x meters from the center of this conductor. Now, let us write the electric field intensity at point P. So, see the electrical field intensity. The electrical field intensity at point P, so due to this charge QA is E equals to QA by 2 pi epsilon naught x, which is volts per meter. So, after writing the electrical field intensity, we can easily write the potential at this point, which is V equals to QA by 2 pi epsilon naught x integral R to infinity dx by x. From the surface of this conductor to infinity, we can integrate this electrical field intensity in order to get the electric potential. As you are moving from the surface of the conductor to the infinity point, this voltage will be reduced to, this field intensity will be reduced to 0. So, in order to get the total potential at that point, we need to integrate this field intensity. So, after integration, you will get the potential. Now, let us see the potential at a conductor due to a group of charged conductors. So, see here, we are taking A, B, C and up to some M conductors. So, distances are DAB, DBC, DCM and DIM. If you write the potential difference between conductor A and conductor B, then VAB equals to, by applying same thing, writing field intensity and integration of the thing, you will be getting the potential at that point. Here, potential difference between A and B, that is VAB equals to 1 by 2 pi epsilon QA into charge of conductor A into ln of DAB by RA, where RA is the radius of conductor A and DAB is the distance between A and B. Similarly, plus QB into ln of R by DBA. Where RB is the radius of conductor B and DBA is the distance between B and A. QB is the charge of conductor B, plus QC into ln of DCB by DCA. So, plus so on, plus QM into ln of DME by DMA, where DME is the distance between M and B and DMA is the distance between M and A. By taking all these, we will be getting the potential difference between A and B. Similarly, if you write the potential difference between A and C, 1 by 2 pi epsilon into QA into ln of DAC by RA, where DAC is the distance between A and C and RA is the radius of conductor A, plus QB into ln of DBC by DBA, where DBC is the distance from B to C and DCA is the distance from C to A, and QB is the charge of conductor B, plus QC into ln of RC by DCA, where RC is the radius of conductor C, DCA is the distance between C and A, plus QM into ln of DMC by DMA. Distance between C and M is DMC, distance between M and A is DMA. So, by taking all this and by simplifying, you will be getting the potential Vs. Now, let us see the capacitance of single phase 2-wire line. So, let us take two conductors which are having radius of R meters, and the charge on conductor A is plus Q, charge on conductor B is minus Q. Distance between two conductors is D meters. If you write the potential at conductor A, then it will be Q by 2 pi epsilon naught integral R to infinity dx by x minus, now potential at conductor A because of charge QB, charge on conductor B is minus Q by 2 pi epsilon naught integral R d to infinity dx by x. That first term is related to the potential at conductor A because of its own charge. That first second term is the potential at conductor A because of charge of conductor B. Now, by simplifying that, Q by 2 pi epsilon naught ln of d by R. So, after getting the potential, So if you now let us write the potential at conductor B, which will be Vb equals to minus q by 2 pi epsilon naught integral r to infinity dx by x, which is the potential at conductor A because of its own charge, plus q by 2 pi epsilon naught integral d to infinity 2x dx by x. Now this is the second term is the potential at conductor B because of charge of conductor A. Now after simplifying this, it will be Vb equals to minus q by 2 pi epsilon naught into ln of d by r. So in order to get the potential difference between A and B, so VAB equals to VA minus VB. It will be 2VA here. Now it is 2q by 2 by epsilon naught ln of d by r. Now finally the capacitance will be potential per charge per potential. So it will be pi epsilon naught by charge gets cancelled, pi epsilon naught by ln of d by r. So this is said to be the line to line capacitance. If you want to write the line to neutral capacitance, now see the potential as if V is the potential between A and B. If you take a point which is exactly at midpoint between A and B, then the potential of one conductor with respect to this neutral point will be halved. It will be halved. It will be reduced to half as the total potential. If the total potential is V, it will be V by 2. As this point is at the midpoint between the two conductors. As the potential is reduced to half between one conductor with respect to neutral, the capacitance will be doubled because the capacitance is inversely proportional to the potential. So in that way, the line to neutral capacitance can be obtained by simply multiplying the line to line capacitance with 2. So as the potential is being reduced to half, capacitance will be doubled. So the line to neutral capacitance will be CAN equals to 2 into CA. So now it is 2 pi epsilon naught by ln of d by r farads per meter. In this way, we can derive the expression for capacitance in case of single phase 2 wire line. After getting the capacitance, you can easily write the capacitive reactance, which is 1 by 2 pi fc. Now let us derive the capacitance of 3 phase overhead transmission line. So let us, for symmetrical spacing, let us take 3 conductors A, B, C, which are separated by uniform distance d. So if you write the potential difference at conductor A, which is integral r to infinity q by 2 pi epsilon naught x dx, which is the potential at conductor A because of its own charge, plus integral d to infinity qb by 2 pi epsilon naught x dx, plus integral d2 to infinity qc by 2 pi epsilon naught x dx. So first term is potential at conductor A because of its own charge, second term is potential at conductor A because of charge qb, third term is potential at conductor A because of charge of conductor C. Here we have taken that the assumption is symmetrical spacing. Here the case is symmetrical spacing. That is why distance between A and B is d, B and C is d, C and A is d. Now, assuming that the system is balanced, QA plus QB plus QC will be 0. So then by taking the integrations and by keeping the integration limits, we will be getting A equals to QA by 2 pi epsilon naught ln of d by r. If you write the capacitance of conductor A with respect to neutral, then it will be Ca equals to charge per potential, so which will be 2 pi epsilon naught by ln of d by r. Similarly, if you write the capacitance for conductors B and C, you will be getting the same formula, that is Cb equals to Cc equals to ln of 2 pi epsilon naught by ln of d by r. It will be 2 pi epsilon naught by ln of d by r. Now if you see the capacitance expression for 3 phase unsymmetrically spaced transmission lines, here for unsymmetrical spacing, here we are applying transposition. In the previous lectures we have explained about the purpose of transposition in case of unsymmetrical spacing. Here conductors are under transposed, so A, B, C in the first section. In the second section A goes to position of B. In the third section A goes to position of C. In this way positions are altered. If you want to write the total potential of conductor A, you need to write the potential of conductor A in position 1 of section 1. You need to write the potential of conductor A in position 2 of section 2. Similarly, you need to write for position 3 of section 3. In the final step, we need to take the average of all these potentials. So potential of in the first position is V1 equals to 1 by 2 pi epsilon naught QA into charge of conductor A into ln of 1 by R, plus QB into ln of 1 by D3, plus QC into ln of 1 by D2. if you write the potential of conductor A in position 2 of section 2 in the second section, it will be V2 equals to 1 by 2 pi epsilon naught QA into ln of 1 by R plus QB into ln of 1 by D1 plus QC into ln of 1 by D3. If you write the potential of conductor A in position 3 of section 3, so which will be V3 equals to 1 by 2 pi epsilon naught into QA into ln of 1 by R plus QB into ln of 1 by D2 plus QC into ln of 1 by D1. See, by taking the average of all these values V1, V2, V3, we will be getting the total potential of conductor A. VA will be 1 by 3 into V1 plus V2 plus V3. So, which will be equal to 1 by 6 pi epsilon naught QA ln of 1 by R cube minus plus QB plus QC into ln of 1 by D1, D2, D3. So, as the system is balanced, QA plus QB plus QC will be 0. From this, I can write QB plus QC equals to minus QA. So, taking this in the above step, so the total potential VA will be 1 by 6 pi epsilon naught into QA into ln of 1 by R cube minus QA into ln of 1 by D1, D2, D3. Further simplification gives QA by 6 pi epsilon naught ln of D1, D2, D3 by R cube. By taking this 1 by 3 to the ln of D1, D2, D3 by R cube term, then it will be QA by 2 pi epsilon naught ln of D1, D2, D3 by R cube whole power 1 by 3. Now it will become QA by 2 pi epsilon naught ln of D1, D2, D3 whole power 1 by 3 by R. So now capacitance of A with respect to neutral is C equals to charge per potential. Then charge gets cancelled. It will be 2 pi epsilon naught by ln of cube root of D1, D2, D3 by R. So this is the expression for capacitance of conductor A, which of unsymmetrically spaced lines which are under transposed. If you see the expression for conductor B and for conductor C, we will be getting the same expression. Next, if you see the example, let us solve an example. A 3-phase 50 Hz 132 kV overhead line has conductor diameter of 4 cm, arranged in a horizontal plane as shown in figure, supplies a balanced load. So assume that line is completely under transposed. So transposed case, find the capacitance to neutral per phase per kilometer. See the diagram, it is of unsymmetrically spaced. Distance between A and B is 4 meters, B and C is 4 meters, between A and C is 8 meters. See the formula for capacitance. So, if you calculate the geometric mean distance, that is dm equals to q root of dab, dbc, dc. So, now capacitance equals to that 2 pi epsilon naught by ln of d by l. That 2 pi epsilon naught, if you simplify that, you will be getting epsilon naught is 8.854 into 10 power minus 12 and pi value and into 2 value. That gives 0.0555 by ln of dm by ds. So, dm you can calculate by taking q root of dab, dbc, dca, and ds is here 2 into 10 power minus 2. So, the diameter is given, by taking by 2 you can get the radius. So, capacitance will be 0.01 microfarads per kilometer. Here students can be asked a question, derive an expression for the capacitance to neutral per phase per kilometer of a 3-phase overhead transmission line when conductors are of equilateral spacing. Thank you.